by Civil Department Association, Force of College of Engineering Pathaнаpuram. Kindly raise your doubts regarding the topic in the YouTube comment section and we will be sharing it with Miss and she will clarify it at the end of the section. I'm glad to introduce the lecturer of this webinar, Engineer Neetha Vasan, and let me give a brief introduction about Senior Microclimate Engineer at RWDI Consulting Engineers and lives in Arizona, USA. She has a bachelor's degree in civil engineering from TKM College of Engineering, Kollam, and master's degree in building engineering from Concordia University, Montreal, Canada. She started her engineering career as a trainee at the Kerala Police Housing and Construction Corporation Limited, Trivandrum. She has since executed projects in 6 continents and acquired more than 10 years of consulting experience in wind, microclimate, and engineering. As part of expressing her passion in the field, she is an active leader in the technical workshops, educational outreach programs for clients, students, and fellow engineers. Now let me welcome Miss to the webinar. Welcome, Miss.
Hi, everyone. Can you hear me okay? Goldie?
Yes.
Yes, ma'am.
Okay, good. Thanks. Hi, everyone. Let me begin by saying that I am passionate about my area of work and equally passionate about sharing that knowledge. So thank you for your interest in today's topic, and thank you, Goldie, for that introduction. So as Goldie said, I am a microclimate specialist. It's one of those designations that you dread telling people when they ask you what you do. No one I talk to knows what microclimate is. So they catch on to wind. Oh, so you design windmills. But that's not what I do, unfortunately, or fortunately. I work with buildings, actually. In fact, I have never worked or studied a windmill, except when my friends and I made this out of food packets for a charity competition. We lost miserably. So now, with technology and the internet on everyone's fingertips, I thought, what would one do when they came across a word for the first time? I would search on Google. So I decided to Google wind engineering in India. And lo and behold, I get wind power, wind energy. So that's all windmills. But that's okay. I modified the search and typed in wind engineering in the built environment. So that should show buildings, right? More wind energy. Well, a little success. That one shows exactly what I searched for. And then this link also said wind and engineering and a few little other keywords, but most of it still led to wind energy, basically. So I decided to modify my search one more time and decided to keep it simple, just wind engineering. It's a broad term, so that should bring up all different types of wind engineering fields, right? Nope, more windmills. I mean, I can't blame my relatives or friends. Even Google doesn't get me. So wind engineering is more than just wind turbines, but not a lot of people know that, and obviously that's clear. So friends, let me wipe all that off and allow me to introduce you to the real world of wind engineering beyond wind turbines. Wind engineering is a complex and unique field, and even so, I will try to make this session as easy to follow as possible. I hope that this session will be informative and not technical. So the agenda is simple. We'll look at who can become a wind engineer, what a wind engineer deals with, and how wind engineering projects are assessed. So, question, who can be a wind engineer? And let me present myself as an example. As Goldie introduced me in the beginning, after graduating in civil engineering in Kerala, it was actually by the power of social media that I got the opportunity to work at RWDI Consulting Engineers in their structural wind engineering team, and that too in my own hometown, Trivandrum. At the time, I knew nothing of this field or the company or what they did. I simply honestly just responded to a friend's friend who forwarded the job opening to me, and luckily I got in. That was my introduction to the field of wind engineering. And before RWDI, I was set on pursuing a PG course in transportation or geotechnical, one of those traditional fields. But understanding more about this area actually motivated me to pursue a non-traditional route, and I left the job to do a master's research in wind engineering. And this is a photo of this photo here is of my team in the wind engineering lab, and we're sitting inside a wind tunnel. We'll look at wind tunnels later, but I just wanted to show you how small the team or how small the group was. In a university of thousands of students, that was the wind engineering team. And I feel that it's because of the lack of knowledge about this area, and even outside India. So I finished that and applied back at RWDI in Canada for a position with their microclimate team, because that's where I did my master's and it was easy access at the time. And the microclimate area was where I wanted to work. So that was it. RWDI Canada was a team that worked in that field, and I applied there. So that was the path, or that is the path to where I am today. That was my path. And throughout this journey, I've worked with some brilliant people, and I'd like to share some of their profiles with you as well, hoping that'll give you a little more information or a little more insight into how people get here. So most of my colleagues have a civil engineering, mechanical engineering, or environmental or aerospace engineering background. And not all of them have a master's degree. And out of those who do, very few are specifically in wind engineering. So that's one example. And you'll notice that most others don't have a specific wind engineering degree. And I'd also like to point out that these two profiles are the most common that I've seen with people who I've met in the field. There is a misconception that you have to be specialized or have a specialized degree to be in the wind engineering field. But clearly, you can see that these two profiles show undergraduate or UG and PG degrees that are not in uncommon areas. They're pretty traditional or well-known. But something to note is fluid dynamics is the key. There is an overlap among all of these profiles, and that's fluid dynamics and structural dynamics also, if that is the area that you would be interested in. We'll move on further, and you'll see that there are many other fields in wind engineering that you can pursue. This is just one of them. So what I was trying to say is, if you understand fluid dynamics and you understand wind flow, then that's that. They're both almost the same, because wind is air and air is a fluid. And here are some universities and organizations in India that have been known to do research in the area, and some commercial organizations that deal with buildings and energy as well. So those are, I guess, they provide work opportunities if people are interested. Now, a lot of other universities also do work in the wind engineering field. They do experimental and full-scale research, or some of these do experimental research. Actually, the first 4 do experimental research. They're universities or organizations. Other universities do analytical or numerical and computational research and development. But the interesting thing, or actually something to know, is that most of these organizations or actually universities, you can simply search on the internet and you'll see that most universities or large universities in India have some sort of affiliation with a wind engineering stream or a wind tunnel, actually. But when it comes to research, wind around aircrafts. Oh, I also forgot to mention that many of these, or most of these universities, also these and those that are not, many IITs that are not listed here, also provide aerospace programs. But like I said, when it comes to research, wind around aircrafts that are high up in the atmosphere and buildings and people who are low on the ground are very different. So, which is why I listed just the 3 universities that, at least to my knowledge, they do have. They're called boundary layer wind tunnels that are able to do work around or look at wind flow around people and buildings that are low on ground. So, what is wind engineering? I'd like to point you to a short poem that little kids in a kindergarten nursery kind of compiled. It says, Wind may be helpful, or actually that even defines wind. Wind is air that is moving fast. Wind may be helpful. It can turn windmills. It can dry clothes on a line. It can push a sailboat. It can fly kites and balloons. It can help seeds grow. It can help frisbees fly. Wind may be harmful. It can blow off your hat. It can blow your hair. It can blow a house or a car. It can also blow trees. So that little poem actually summarizes the 20 odd slides that I'm going to show you in the next few minutes. So when it comes to buildings and wind, again, wind low, close to the earth, where buildings, people, and wind, we all live, there is the relationship between wind and buildings is bidirectional. Wind applies force on buildings and creates wind-induced structural and cladding loads and other related effects. And in turn, buildings alter wind flow from its otherwise unobstructed path, I would say, quite like water flowing around rocks. And this interaction affects microclimate, or the climatic conditions that are low to close to the earth and close to the ground and right around us and around the buildings themselves. So let me give you an introduction about of some general wind flow mechanisms that we come across pretty much on all building projects in one form or one level of severity or the other. When wind is obstructed by a structure, such as a building, it will find the path of least resistance to continue along its way. And in this process, it will flow around buildings or any obstruction, and it'll create high wind activity zones around the building. So anywhere you have a corner, typically a sharp corner, like around the building, those are regions that winds would be moving faster than usual, or faster than somewhere else along the streamline. And this sort of flow pattern is called downwashing. And some of this flow also moves upwards and over the building, and that would cause wind accelerations and high forces at the edge of the roof over there. So these are the kind of flows that we would have to look at if there were rooftop structures like solar panels or a pool. Like very tall buildings sometimes have pools and decks and outdoor restaurants up there. So those are the kind of flows that would affect that region. Now, majority of the flow is directed downwards and around the building. And that's typically where the highest wind activity would be seen. Now, this effect, this downward flow and flowing around, could be intensified if a short building is located right behind. Or when I say behind, it is downwind, as in, upwind, as in before the building, relative to the direction in which winds are approaching. So when in that kind of a scenario, this downwashing, the intensity of flows down below can be increased or just exaggerated. Now, similarly, if a similar kind of intensification of or high accelerated flow could be seen when winds are flowing between, let's say they approach in a more open environment and then they have to squeeze between two buildings or two structures. It's kind of like, it's basically Venturi effect that you've probably come across in fluid dynamics. That's exactly what's happening here. Flow through a funnel, and that's what happens here. So small area of cross section, high wind velocity, high flow velocity. So that's typically in the industry, it's called a Venturi effect, funneling, or channeling. And similarly, now this was a horizontal type of flow, and similarly, these kind of accelerations do happen under bridges as well. So these are very generic and typical flow patterns that are seen. Pardon me. So these are typical flow patterns that are seen, and we'd look at this and all other kinds of flow patterns around buildings when we deal with the project. So The reason I showed you this is as we move to other slides and move on, I will be mentioning these, I'll be referring to these words once in a while. And so the slide hopefully gives you an idea of what all that means. Now, like I said, these are some common mechanisms and it could happen all on its own. But, typically buildings don't stand just on their own. You have buildings, other buildings around it. Typically, if there's a high-rise structure, usually you'll see it in a cluster of other high-rise structures also, or even shorter buildings. It's always you have a cluster or a group of buildings, and it's easy to draw these diagrams on one building or individual buildings. But when they all come together, all of these types of flows also interact with each other, and that becomes even more complicated and could result in undesirable wind activity in the pedestrian realm, which is where we are, on the roads, on around building corners, on sidewalks, etc. Now, that would all depend on the local weather, the climate, and the type of buildings, the orientation of the building with respect to the winds in the region, etc. But we'll get to that in a minute. So, like the poem said, wind can be a friend or a foe. Now, who doesn't like a nice, good breeze on the beach or just outside in a park? It's always nice, especially when we're in a warm climate, right? When it's a warm, humid climate, a breeze is always nice to feel comfortable. Winds are also helpful when it comes to sports activities, like in water or paragliding or other similar activities. And wind is important for air flight operation as well. And obviously, it's important in windmills because that's all people know about wind engineering, unfortunately, or fortunately. But then winds can also be problematic. And one of those issues, or I guess the simplest issue that I can point to, is too much wind being a nuisance, especially extremely strong winds that do not happen every day, but it could be maybe once in a year, once or twice in a year. Maybe you have a rainstorm or just a particular windy day, and that just in general, those kind of activities can cause inconveniences to people. And this may look like, we could say they're simply inconveniences, and that's okay for us. But when it comes to extremely expensive projects like a high-profile, multi-million-dollar hotel where VIPs have their business meetings or parties, in those kind of scenarios, even these little inconveniences can be a big issue. Too much wind, like I said, could also cause actually dangerous situations. Like this is a video playing, and you'll see how it's already a windy day, considering how the tree leaves were blowing, and then you have this temporary wall structure topple over people, actually. Now, these are some extremely, dangerous situations that ideally shouldn't happen. If, let's say, the wall was designed to be, even though it was temporary, if the people who put that there were aware of the kind of wind flows that could have happened there, maybe other precautions or more reinforcement might have been used. Now, with respect to that video, as you see, people were rescued. They sustained only minor injuries, and even that child who was there was okay. So in the end, good news. Now, on the opposite end of the spectrum, even too little winds, especially in hot climates, can be uncomfortable. Now, not only is it unfavorable with respect to the heat, like in the Middle East or maybe even Delhi or other, where you have extreme heat issues with very low humidity, it could be a huge problem. And obviously, people are looking to get some sort of a breeze. And when you have a lot of buildings or structures, and as modern urbanization, just keeps growing, you'll see that there are more and more tall buildings. Right now, if you look at let's say Mumbai or Delhi, every day you have a new project coming up, and it's a high rise. So it could get to a point where, although now things are okay, a lot of buildings can come up and then restrict wind flow amongst those buildings even further. So those are situations where too little wind can be problematic. This is an example of how, or actually it fits the context, because a lot of new high-rise buildings right now are steel or concrete framed, but they have a cladding around them. A cladding, as in, it's more like a shell that's made of glass, like steel and steel frame and glass, and they're made in such a way that they have to withstand. They can, to some extent, they have their own bending moment and motion properties, dynamic properties. So in these cases, this is just a building corner that's being shown. When, depending on what direction winds are acting, it could impact a positive or a push force onto these elements. It could impact a negative or a pull force, or it could be a combination of both. In any case, moderation is always best, right? Extremes of any of these influences can create damages, like this example shown here. So this was a building that it is not under construction. It was a building that was fully clad with glass, and during a hurricane event, a lot of that broke. And so after that, they started construction once again. Yet another area where wind could be, wind is an important factor, is structural loading. So we learn about dead loads and live loads and static and dynamic loads. Wind is one of the natural dynamic loading sources that we'll come across. And probably any senior students attending this webinar might be familiar with the IS 875 code, part 3, where that talks about wind engineering and wind loading. Now, codes have to be very conservative, because they can't, you can't have a documentation for every possible design scenario. So that's scenarios. Those are situations where when you have, there are situations when you have complicated building designs, not simple structures, and that's when sometimes the code may be overly conservative, and you might have to look at experimental approaches to get a more optimal, cost-effective design. So back to structural loading, wind, as I said before, applies a force on buildings, and it could be shear forces, overturning moments, torsional moment. All of these are things that need to be considered when building a tall building, typically a tall building. Now, I know you can't hear the audio too much, but I'll explain what this is. This is Tacoma Narrows Bridge in Washington. This was an event that happened in 1940. It was, you saw that the bridge basically fluctuated. It was shaking like a ribbon, and then it fell apart. No one was hurt, because there was a good amount of warning. People knew that this was going to happen. Engineers knew that this was going to happen just before it did. And so the road was cleared. All precautions were taken. And it happened because it was one of the earliest recorded failures due to wind. So as you can see, I'm kind of listing a number of problems that can be associated with wind. We also, in some occasions, have to, depending on the area, depending on the situation, and depending on what region you're in and how windy it could be, we'll have to look at vehicle stability. So large container trucks like these going on bridges in the mountains, maybe, that are very, or in bridges above a wide river, so those kind of situations, there is always a possibility that if we're not careful or if you're not aware of the wind conditions in the area, there is always a possibility that such large vehicles with large surface area can be toppled over easily, because there's a large area for wind to apply a strong force on. Exhaust reentrainment. Now, building exhausts are not something that's commonly looked at. Structural and cladding and comfort, those get looked at even more commonly among all of the areas that I'm going to talk about today. Exhaust may be important, more so in, say, healthcare buildings or labs, where that exhaust pollutants and unhealthy fumes that people don't want to inhale. It affects the air quality around the area. And that's something that we look at a lot of the times. Now, these figures show wind direction, and the red particles are how exhaust fumes are modeled. And these are just some scenarios showing how exhaust from one building, over here, the top left, one building can be entrained into another building if the wind direction is unfavorable, let's say. For humans, it's unfavorable if this happens, or it could be self-containment. So it could be that the exhaust from the building gets back into the building through the windows on the opposite side, or both, a combination of both. Where this is relevant, snow drifting is a huge area of study. The problem is snow, especially in colder parts of North America, wind flows in high volumes, and then it gets. Sorry, did I say wind? Snow falls in high volumes, and the wind can carry it to locations that are undesirable. So in this example, we're seeing snow falling on the roof of a building, and that was a problem for the clients because they had to. This becomes another load that the building needs to be designed for, and I guess at the time they hadn't designed for the kind of load that they were seeing after the building was built. Weather changes, climatic changes, all that led to unexpected amount of snow. And then this is, on the left, you see how it was modeled in in our lab. You'll see that it's pretty accurate in terms of the amount of snow that's collected on that particular surface. So these are one type of issues. Now, where snow is not an issue, sand could be an issue, especially in the Middle East and other desert climate areas where there's a lot of dry sand and undesirable accumulation. Similar to what I explained for snow, undesirable accumulation could happen with sand also. So this example actually shows damage to tracks, rail tracks that run across acres and acres of desert area. That sand infiltration could damage the functioning. It could affect the operating of these tracks, and even roads. Depending on the amount of sand and sand that gets deposited on the roads, it could render the area unusable, which again, cost, time. That's all a problem there. On the right side, the two images show mining and dredging areas. Now, in mining and dredging areas, dust, especially if the climate is pretty dry, dust is an obvious result of the work. That there's no escaping that. And now, on top of the existing nuisance, if wind also becomes an issue, it could just intensify the existing problem and affect their operations and people's health to a dangerous level. So that was another problem that we may have to deal with as wind engineers. Now, I'll get to how this may seem silly in a bit, but this is wind-driven rain management. So rainfalls are common in many areas, but there may be infiltration of rain into the building. And that's something that some of our clients want us to look at. They want to see, obviously they don't, it so happened that the building was not designed to be wind responsive, or these issues sometimes are not even things that you can think of in advance. So when the problem arises, they come to us, or sometimes they know that there will be a problem, so they come to us in advance. Basically, it's rain infiltration into frequently used spaces. So it could be an outdoor space, like under those columns, like shown under the building there, or it could even be through windows or little like walkways under the building, depending on the design. Now, like I said, Some of these issues may seem silly considering like we are in a place that we get a lot of rain. But when it comes to, like I said earlier, multi-million-dollar projects like a hotel or a business center, any little factor that causes an inconvenience to guests means a loss in sales. That is, loss for the investors or owners of the project. So when the project costs are high, losses and savings can be proportionally high, of the order of millions. So that's why we see these kinds of projects come to us, and there's science and research that has gone into trying to solve these kind of problems. Of course, the problems are not common all across the world. It varies from place to place. This is an example of waterfront projects. So you'd have to look at winds near waterfront projects, because sometimes it could be for a harbor design, for a port design. Basically, wind creates waves, and wind affects sailing and berthing of boats and ships. So that all comes into factor, and sometimes we have to look at these kind of issues also. Baseball or ball trajectory is another area that we often look at. It need not be baseball. It could be another sports field. Basically, how would a ball trajectory be affected considering the wind in the area? Again, it may not be a big issue in low wind climates, but in places like Chicago or Texas, they have a lot of stadiums and a lot of games, and this could be an issue there. So sometimes it's just proactive design, in that people just want to do a good job and make sure that they're designing a project, especially when they're investing so much money into it. They want to make sure that they're creating a project that will not face too many issues that may be difficult to solve later on. So sports aerodynamics. If you're in the mechanical engineering field, or even civil, any engineering field, I mean, you may already be familiar with race cars and even commercial cars being tested in a wind tunnel for their efficiency, for their streamlines, or for their dynamic property in wind. Now, athletes and vehicles, especially in sports, they move against wind, or even otherwise, they have to position their bodies or design vehicles to be as streamlined as possible to be able to move with the least possible air resistance. So knowledge of airflow and fluid dynamics plays, and especially local weather and climate, it plays a big role in such projects. We often see a lot of unique projects that have unique problems also. For example, the left image shows it's the National Museum of African American History in the States. It's shaped. It's interesting in that it's a simple building on the inside, but the outer cladding is made of a metal mesh, and they wanted to replicate an African sort of crown design. Now, sometimes when you're dealing with mesh materials or perforated materials, and the wind happens to be at the right speed and at the right angle, this building whistles. It may sound strange, but if you've tried blowing over the opening on a bottle, you can whistle that way, right? Same effect. Wind blowing parallel or just at the right angle to these perforations can create a sound, and it's not one little tiny opening. It's a cluster, it's a mesh, it's a network of openings, and the sound that it generates can be pretty disturbing for people who are walking in the area. So strange issues, unique projects, that's what they are. And believe it or not, we have actually been asked to look at parade balloons. So these, and I know it's not the culture everywhere in the world, but there are places where these parades are huge, and every year the balloons keep getting more complex and more balloons, more bigger and more just fancier, I want to say. It's like firecrackers, every year you get a more splendid display than the last year. These balloons are the same way in some places, and they're so big and so heavy and also so dangerous that if they're taken out on the wrong day with the wrong kind of wind conditions or weather conditions, there have been incidents where, I think this example itself, or maybe it was just the city, where the balloon got like out of control. It broke off from the guy lines that were holding it down, and it hit a lamppost and basically showered powdered glass on people. That's not a good situation to have, especially when there's a public event going on. So again, another unique, interesting problem that we sometimes get to look at. I want to list these out as well. These are like landmark projects in India that we worked on, other than normal buildings, like high-rise buildings. These, I want to say, are some interesting projects that we've worked on. Vrindavan Chandrodaya Mandir in Uttar Pradesh. It's actually the largest. It's the world's largest tallest temple, not the largest. It's the world's tallest temple. It's about I want to say 210 meters tall, which is like 70 stories. You know, your usual buildings, even say Kim's Hospital in Trivandrum or other buildings around here, you go like 9, maybe 10 stories, and this is 7 times that height, and it's a temple in Uttar Pradesh. And the next image on the right is the Statue of Unity. It's actually the world's tallest statue. That's also in India. It's in Gujarat, and it's around 180 meters tall, which is about 60 stories, if you wanted to compare that to a building. They're all pretty massive structures. So the height and massivity, like considering the height and massivity of these structures, they have to withstand a lot of wind. And these bigger the structure, greater the wind amount of air it redirects. And so the clients did a responsible thing by trying to make sure that the redirected winds don't have a negative effect on the surroundings and also on the structural loading side of things. So when all of these studies come together, sometimes we get a huge master plan projects where a client or a city is developing a huge area with a lot of buildings. And again, they want to be proactive and make sure, especially if it's in a high wind area, they want to make sure that wind doesn't flow around or through or in between the buildings in a way that it would create a lot of bad vibes, like bad or unfavorable wind conditions. So in this animation here, blue and green represent some of the lower wind speeds that that are appropriate for streets and sidewalks or where people walk, and then the yellows are also tolerable. It's okay, but red zones are no. We want to create as few red zones, and if there are any red zones or high wind zones, ideally they should be far away from anywhere that people would walk. And so you'll see in this animation again that right around the tall buildings are where those red zones are the biggest. And then within the cluster of buildings, things are a lot calmer, but then there are these small local areas, even within that large cluster that could get pretty windy. People also want to make sure, especially if it's a low wind climate area where there's a lot of high-rise buildings coming up, that the cluster isn't arranged in such a way, or the cluster of buildings, or the development isn't designed in a way that it would restrict all sorts of wind flow coming into the area. And especially in a hot climate area where you want natural ventilation for sustainable design and cost-efficient design, no wind or low wind is also a problem, like I said before. So that was master planning. Now, we know that there are all of these different types of problems that can come up. How can we assess them? How is it done? Now, the study and manipulation of the behavior of wind around anything, like on the environment, people, natural and built structures, that's basically wind engineering. And because you're dealing with wind, obviously you'd have to look at the weather or climatic conditions. Climate data is what you want to look at. I shouldn't be making this mistake, but I keep saying weather and climate in the same sentence. Weather is what's happening now or over a very short duration of time. Climate is what happens over a long duration of time. So you could say that the weather today is cloudy, it's going to rain, but the climate in Trivandrum is usually warm, and it rains several times a year. So that's
So long-term effects are called climate, and weather is short-term, today, tomorrow, yesterday, those kind of things. So first thing we'd look at, because this is a wind study, is meteorology and climate analysis. And depending on the project and the issue that we're going to deal with, or the demands of the client or the project, the weather modeling or the climate assessment that we do could be at a very large scale, like a map of wind climate in a large continent or a country. It could be somewhere in between, which is looking at local weather in a particular city, like weather or climate, wind climate in Trivandrum or wind climate in Mumbai. They are different, but it could be that way. Or again, depending on what you intend to achieve, it could even be at the occupant scale. Basically, what are the wind flows in your balcony, for example, or air movement in your balcony. So the scale is huge. And because it could be anywhere from a continent or like a regional scale to an occupant scale, we have to be aware, and we have to be educated enough to take the decision as to how much effort or what level of expertise or what level of assessment or research do we want to put into getting this data. Wind assessments are typically based on statistical and probabilistic model of wind climates. Wind climate varies from place to place, so it is important to acquire data from reliable sources located close enough to the project site so that the source data is representative of a climate at the site. For example, if you're doing a project in Trivandrum, you don't want to take the climate data from an airport in Delhi, right? You want it to be as close to the site as possible, and airports are actually the most reliable sources that are and that's because airports deal with aircrafts, their equipment and data quality are, the anemometers or the wind measurement or the climate recording, weather recording devices in airports have to be monitored and maintained well because it's important for air traffic control. So for that reason, airports are the most reliable sources for climatic information. Now, the sources also should be able to provide long-term records. So because this is statistical analysis, it has to be, the records have to be preferably readings recorded every hour for at least 20 to 30 years. So that's a long period of time. And you may not get that if you're looking at a relatively new meteorological station located somewhere else. Airports are also meteorological stations, or anemometers at airports are also, because of the design of airports, they're also located in very open surroundings. There's almost nothing around it that would disturb winds that are approaching the anemometer or the instrument that's recording wind speeds. That's also important because we want unadulterated, clean wind data that is recorded every hour and maintained well. Now, wind data can be represented by wind roses, as you see here. The sectors indicate the blue lines, or the sectors around. So the compass, around the compass, you see wind directions or directions of approach. So NNE means north, northeast. That's north, south, west, and east. And these represent directions from which winds are approaching the site, or the airport, which is at the center of the compass. Now, not only does wind data, like I said earlier, wind data varies from place to place. It's different from place to place, but it could also be different from season to season. So let's say around May to October, if I call that summer, this is a station where summer winds are predominantly from the south, and winter winds are predominantly from the north. So if you're designing, this could be a little confusing if you're designing like a beach restaurant type area. Like in the summer, you're sitting out at the beach, and maybe your winds will be blowing straight into your face and giving you a good breeze, but also a lot of sand drifting. So, and in the winter, there may not be any breeze at all because you're sitting on the wrong side of the building with respect to where winds are approaching from. So the data has to be accurate, your design has to be appropriate, and the decisions that we make are only as good as the data we have. If the data quality is wrong, then really our decisions or our interpretations of wind conditions at an area might be misled also. So that was seasonal variation in winds. Now, winds could also just vary in terms of where strong winds approach from. So this is, again, we filtered the data as like this wind row shows all of the winds approaching this particular airport. And then we filtered out winds that are stronger or speeds that are higher than 20 miles per hour. These are considered strong winds that have the potential of creating undesirable or uncomfortable or even potentially unsafe conditions, depending on the building design. And we see that one would like download a wind data or wind rows from a reliable source, and you'd see all wind speeds are actually, most of the wind speeds are coming from the south. And so it's easy to be misled to design for that information. However, only a knowledgeable person or someone who knows that there is this possibility, who has some experience in the wind engineering field, would know how to filter out that data and look at strong winds and design for that also, or consider that into your design also as appropriate. Yet another wind rows I'd like to show you. So we saw seasonal differences. We saw differences in directionality of based on wind speeds. But then here's another example where wind speeds are actually varying within a single day. This is actually in the Middle East, and an airport that's located very close to the ocean. Land breeze and sea breeze, I'm sure you're familiar with the concept. That's what's causing this differences. So again, if someone were not to filter the data and check all of these things, it's easy to assume that, if you combine all of this information, you probably will get see that most of the winds are coming from one quadrant, one single quadrant, let's say the north directions, but then it changes throughout the day. So just some things that we, as wind engineers, have to look at and be aware of before diving into a project. So once we have the wind data, we then can look at how we can approach this project depending on what is at stake or what your problem is. So I'll go across a few common methods or methodologies that we use to assess wind projects. First one I'll talk about is a desktop or design review. Now these are very high level assessment tasks where sometimes you don't even have you don't have an actual physical model of the building. You're just looking at drawings, maybe a 3D model or photos of the building, or sometimes even looking at the building in person. Maybe it's an existing building with a problem. You either go to the building, to inspect it, see what's going on based on your client's complaints, or you have drawings of a building that is to be constructed, but they're anticipating or they just want to do a good job and see if there will be any wind issues. And then you basically look at the drawings and give your opinions of what things might be like. Give your predictions, your assessment of what things might be like around the project. Now, this is only done by highly experienced wind engineers, and that's because it's not easy to take a guess at what can happen. So you'd have to have a certain amount of experience, a certain amount of involvement, have to have seen many different cases to know, to easily just look at something and diagnose it, basically. So it's something like a doctor for buildings, I want to say. So that was desktop assessments and design reviews, and they're typically very quick. They are cheaper because there's not a lot of there is the technical effort is there, but there's no modeling or a lab required. So the resources required to do this kind of assessments are low. So again, low cost. But as a desktop assessment also answers very simple problems or simple guidance. Sometimes the end result or kind of the report for a desktop review or a design review could say, well, I think there are going to be complicated problems with this building. You should do more advanced tests and advanced assessments. So that can happen also. Basically, it's an advice giving stage. Numerical modeling is just the next step where we would use a computer-assisted model or a simple numerical, maybe a program that's coded into BASIC or an Excel macro. So a simplistic way of using equations and establish relationships between wind and buildings and other structures to, again, come at a conclusion about the potential wind effects around the project. The more extensive work is typically done in a wind tunnel. Now, I've mentioned this word quite a few times. The video you're seeing here is of an SLA or stereolithographic machine that is creating or kind of molding the model for us. It's based on CAD programs, 3D modeling programs, where the building is drawn, modeled, and then the information is fed into this machine, and the machine creates a model for us. That's usually done for, typically, it's an expensive process. It's kind of like 3D printing, but not exactly. It's an expensive process. So you typically use it for the study building or the focus building, the subject building in the project, for example, the one right at the center of this disk. So once you have a central building or the focus building of the project, and then you also have to model the surrounding features, features that are surrounding that proposed site. Now, this building doesn't exist. When you're doing a project, this is probably a project that is going to be proposed. So you model that, put it on the location where it will be, and then you also model the existing or the features surrounding it to a certain distance. Now, this is called a turntable. Within this entire containment, it is a wind tunnel. I'll show you another photo in a bit. But this disk where all the model is sitting is called a turntable, and it's called a turntable because the darker wood part, not the lighter part, but the disk itself can rotate. Now, it needs to rotate because we need to blow air and basically simulate wind and blow it at this model, but we need to simulate or we need to understand how the building and the surroundings and how wind itself around the building will behave when wind blows from this direction, that direction, this direction, basically all around the compass. So that's why it's called a turntable, and it rotates. This is another photo, another view of the wind tunnel. So that's, again, the study model, the surrounding, and the proximity model, we call it. And then that's where the fan of the wind tunnel is. So wind would blow from the back or the far end of the wind tunnel towards the building. Now, it is also important, it's not enough to just blow air at a disk. It is also important to simulate all the properties of wind that one would see in real life on the actual site in real world conditions. So again, I promise not to go into too much technical detail, but if anyone wants to know more about this, I can definitely give you answers at a later point. But these blocks that you see here, the spire at the back end, and even there are certain features around the fan that are all designed in a way that if the buildings and if the model is built to a certain acceptable scale for this calibrated for this wind tunnel, wind conditions or the wind will be simulated to be as close as possible to reality. On the right side, top right, you see an image. It's actually the model, and it's the same model, but it's been cut in half, and you see a mess of hoses coming inside the model, right? So what happens is, this is a cladding project. So it could be a cladding or a structural project. Now here, I'm not sure how clear it is, but there are several hundreds of dots on this building, and each dot is a tiny, like a pen nib sized hole, and those holes are what these hoses are connected to. And then the hoses, the other end of the hoses are then connected to a data acquisition system. So when it's all put together, the hoses going inside the model will come underneath the model, and it will go under the wind tunnel over here. And then it connects to the data acquisition system. So when wind blows onto the building, these are say transducers, pressure transducers that convert the velocity into pressure values, and that's what we get as a final result of this test, which we then use for our analysis. That's one sort of instrumentation. And then this is another type of instrumentation that we use for measuring winds at or close to ground. The other type of instrumentation was more on the surface of the building, wind pressure on the surface of the building, and this is more on the ground. So you'll see these black dots on and around the building site, and those are these sensors. These are about 1 centimeter wide in diameter, and the sensors are placed in locations where you want to measure wind speeds at or close to ground. And that's usually used to assess comfort of people. Are people going to be comfortable around a building? Is the building going to redirect winds in a way that it would get so complicated and so windy that it would be a nuisance for people? That's a sort of answers that we're trying to provide through this test. This is a photo of one of our wind tunnels. Basically, and I'm sorry I didn't explain this before, but I was getting to this slide. So a wind tunnel is a long channel. It's a mechanical tool with high-powered fans that blow air towards a model. So basically, it's a big box. It's a long tube. You can call it however you want, and there are fans at the back end of it. Some wind tunnels are designed in a way that the fans rotate and the wind will blow towards the building. And some are designed in a way that when the fans rotate, wind is being sucked in. So depending on how it works, you'd have to understand how to assess this building as well. Because when it blows, you can easily say that that's the direction from which winds are approaching the building. But when it sucks in the wind, it'll be the opposite. Wind would actually be approaching from that direction. So it can be different that way. So this is one of our wind tunnels, and just wanted to show you an example. I'm giving you very brief details right now, but I can answer any questions at the end.
And like I said, the wind tunnels are designed in a way so that the air or wind reaching the disk has all the relevant characteristics of wind that naturally occurs at the site in the real world. And so the data obtained, or the pressure and speed data obtained from the wind tunnel, is then combined with meteorological data, that is wind data collected from the airport. And this combination is then analyzed to help get answers to the problems that we're facing. This is yet another again, mechanical tool used for experimental studies. It's not a wind tunnel, it's a water flume. And some of you may have come across this in fluid dynamics chapters or projects. It works similar to a wind tunnel in that there's flow coming in from that and the far end, and then the model is here at the bottom end of the photo. Water flumes are especially useful when we want to look at particle transport, like the sand and snow transport examples that I showed you earlier. So imagine if we were to do a sand study or particle study in a wind tunnel, you can imagine it will just fly everywhere without a way to control it. So we need a contained system in which we can observe the movement and deposit of particles. And the working idea here is similar to a wind tunnel. That particles and the flow comes in from one end, goes around the building, and wind water is also a fluid. So there are ways to model and kind of translate this motion into how air would behave around buildings. And then the difference here is that the medium is water, not air. So those were experimental devices or experimental tools that we would use to assess measure wind around buildings. We also have CFD is an established tool in the industry, and some of you may be familiar with this as well. For urban wind modeling, computational fluid dynamics, CFD techniques are used to generate a virtual wind tunnel, like we're having a virtual meeting here. It's a computerized wind tunnel, so to speak, where flows around the site, the wind flow around the project and the surroundings and the study building are all simulated at full scale. So in the wind tunnel, everything's kind of scaled down to a small scale, typically 1:400 or 1:300 scale. So it's a pretty small scale. And CFD, because it's on a computer, you can do it at any scale you want. And typically it's done at full 1:1 scale. The computational domain that covers the site and the surroundings, basically the domain that we're looking at, this entire area, the area that we're looking at, is divided into millions and millions of small cells, and in each cell, numerical calculations are performed, or computational calculations are performed, and the flow quality, the flow pattern. Will wind go straight or around a corner? All of these things are established through calculations. The advantage with CFD is that there are no limitations to the number of points. You know how in the wind tunnel test there were dots on the building or dots on the disk on ground where the instruments were installed? There is a limitation to how much you can drill a model or a disk to install these instruments. Whereas in CFD, there's no limitation. It basically gives you results over. It kind of gives you a map of wind conditions across the entire area or domain that you're looking at. So that's another tool we use. The one main difference, though, we talk about in the industry is that at present, at least in today's research and in today's where we stand today, CFD is not equipped to answer some of the more or simulate some of the more complicated wind flow patterns. It may be, but it is also extremely expensive and time consuming. It would need a huge amount of modeling, computer capabilities or power to get to the level of detail that we would get from a wind tunnel test. These are just, CFD results are either shown as just still images of like a wind map, or they can be shown in terms of, in the form of animations like this that show a better visual of how wind moves around the building. And, for this reason, don't be surprised if some people call it colorful flow diagrams instead of computational fluid dynamics. And the last method I'd like to talk about briefly is field tests, full-scale on-the-field tests. Now, as I said before, desktop reviews can be quick and dirty. It can be done with low resources and done very quickly. Wind tunnel testing may take a lot more time because you have to build the model, and it's a quite extensive model. So there are more people involved in making that model. There are people, time, and effort involved in getting the model into the wind tunnel and running the simulation, operating the wind tunnel. That's an additional resource or cost involved. And then obviously there's the engineering side of things. More assessment that goes into interpreting numbers and getting the final results and all of that. So it's a more extensive but also a more accurate process. CFD also has the similar advantages as in it's kind of in between a desktop assessment and a wind tunnel modeling, because computer modeling, for a wind tunnel model, someone has to make these or create these models on CAD to give you an idea of what the building looks like, and then someone else has to construct them. For CFD, you stop with the computer modeling because that's all you need to get to the analysis part of things or the simulation part of it. So it takes a little less time than wind tunnel tests, but the cost can be comparable or cheaper depending on how detailed you go into the assessment using CFD. Field tests are a whole different story. They're only done, or full-scale measurements. If you wanted to take full-scale measurements of a problematic wind condition at a building. Now, you have to remember winds are not consistent. They can be unpredictable. They can happen today. It won't happen tomorrow. So it could be unpredictable. So for that reason, you'd have to wait a long time to get the same consistent readings over and over again. So it could be time consuming. The equipments are bigger, heavier, and of course you have to travel to the site, be prepared for all of that. So field tests are a whole different story, but then it is done where it is required. More so, it's done for existing projects that are facing problems. Sometimes it's just easier if the problem is very consistent in its occurrence. It's easier to just go to the site and take some measurements there, or observe and see or experience it for yourself to give advice for a solution. So those were all the types of methodologies that you would use in assessing wind conditions. Now, so we talked about who, we talked about what, and now we can go to the end section of how we do wind engineering. Solutions. Again, we talked about problems, how we assess them, and then this last section is going to talk about what kind of solutions we recommend for some of these projects. So these are just case studies that I'd like to show you to give you an idea of the things that, what you deal with in a wind engineering scenario. Wind-induced responses. That is basically another way to say loading. Okay, wind loads on a building, or the building's response to wind acting around it. I hope everyone recognizes this building. It is the Burj Khalifa. It's the tallest building in the world currently, and because of its height, and see how slender it is at the top. Now, if you were to put a tall, slender building without proper design into wind, and you have to remember, wind speed gets stronger and stronger as you go higher up in elevation, because there's nothing to block it. And especially in the case of Burj Khalifa, if you look at the middle photo, you'll see it's significantly taller by several orders than all of the buildings around it. So there's absolutely nothing to block winds that are approaching this building at the top. And if not designed properly, almost all tall buildings have the tendency to sway like a swing. It will kind of sway from one side to the other. So imagine this building swaying like that. And if someone were to be at one of these upper stories and to feel that sway, that's not something. Unpleasant is an understatement. You don't want to experience that. So wind-induced accelerations are another issue that we look at when looking at tall buildings like these. So because the wind loading and wind-induced motions, which I explained right now, were expected to be critical. They were expected to be critical in this project. The structural designers of this project brought us in very early on to take a look at how wind would affect this building. So it was well before my time, but I've heard that it was an excellent experience for those who worked on it. So other than structure, there were many tests done on it. It was a unique project. It was the tallest of its kind, and you don't want to go wrong when you're doing something iconic like that. So the design team was very careful, and we did all sorts of tests to understand wind loading, cladding, acoustics, aeroelastics. That's again another area of building response to winds, and also comfort, wind flow at the base of the tower. So all of these petals and the kind of triangle, or that 3 petal sort of design, was positioned, rotated, and it all, many different orientations were looked at to arrive at an optimal design and optimal, even the arrangement of these steps. Everything was done very intentionally so that the building would be a success in terms of its structural stability and wind stability. So at the base of the building, there had to be a lot of landscaping. This is the Middle East, but there had to be a significant effort done so that considering the size of this building and imagining how much wind it would redirect around it. A lot of effort had to be done to make the base and the area around it comfortable for people to access also. Here's another example, similar sort of situation. This is Taipei 101. It is one of the tallest buildings in the world. And at the time, I think it was when it was constructed, I think it was maybe the tallest or the second tallest back then. This is an interesting case because this was also a very tall building in a surrounding area that had very short buildings, so nothing to obstruct wind that would affect the area up there. And what started out as a simple cube sort of tower ended up being notched at the corner. And what seems like a simple change, and the steps, the designs like that, like what seems like a simple change on the drawing board actually significantly decreased the wind response of the tower. So that's another kind of solution that we brainstorm and arrive at. And all of these past projects teach us a lesson also. So as new engineers, when we come across newer projects that may have similar issues, we kind of learn from these past projects and understand, kind of take our lesson from there to apply to new projects. When projects, now this is a bridge, but when projects are located in complex terrain environments, in a city, maybe it's easy to get data, wind data from an airport, and it would be representative of conditions at the site. It would be very similar. But in scenarios like this, where maybe the airport is at a location not in the valley, somewhere else, and wind at this location would be affected by the local terrain around it, which is mountains and complicated like wavy structures or undulating structures. In these cases, we have to take a lot of wind measurements all across the terrain to understand wind conditions a little better. So it's not easy to directly take all pre-recorded data from an airport and directly apply it to the site. You'd have to put this model, actually model the mountains around the site, put it into the wind tunnel, and take measurements on the mountains. It's more extensive. So these are called topography tests, as in you model the topography and you establish how the topography affects wind flow around itself. We're coming close to the end of the presentation. This is not the last example, but we're close, just letting you know. Building reshaping for pedestrian comfort. Now, as you can see from the 3 images and the date stamps above, what started out as a sort of a standard cuboid building ended up being a totally different shape and orientation at the end of this round of tests. Now, it was done because this building is significantly tall in a windy part of the world, and it had the wider face pointed towards the direction from which wind was frequent in the area. So it basically was acting like a boat sail. It would catch winds and redirect it around it, and a lot of it downwards. So downwashing, if you remember from one of the previous slides, downwashing, and that downwashed winds. So imagine a volume of water, a volume of air moving towards a wide object and sloshing around it. That's basically what was happening to the wind in this region. And so across 2 years, and many tests and many discussions and workshops, we ended up with a design that was significantly better than the original in terms of its wind response. Some of the other large-scale measures like this that buildings or designers adopt to ease things or ease wind flow around the base of a building are these complicated steps or notches or like zigzag, just massing, different massing design options or different shape design options that would help confuse winds in a way that when it flows towards the ground or around the building, it isn't as problematic as it would have been if the building were a simple, normal, like standard rectangle. And some of the small scale measures, when the problems aren't that significant, would be maybe to add a few trees where the problem areas are, to diffuse winds in the area, wind screens that are taller than a person's height, again, to diffuse airflow through the area, wind flow through the area, a seating or an outdoor dining space that is enclosed by a canopy and some glass screens on the sides. Again, windscreens, trees, canopies. These are the sort of things that we would call small scale because it's easier to implement than, say, an entire design change like the previous example. This last example is a project in India where the intent was, so it's an example of where early design, very early concept stage design decisions and consulting helped with natural ventilation design on this project. Now, this project is located in a region where winds approach primarily from the east and west. So I'm just showing you the west direction here and then east direction over here. So winds were predominantly from the two directions like that. And naturally, because we're in a tropical hot climate region and sustainable design is considered important by many, they wanted to naturally ventilate all of the areas in these buildings. It was a key objective, and it's sometimes a difficult task to attain when you're not located in an extremely high wind region, or especially when many tall buildings are situated in a cluster where one building will obstruct wind to the other. So this is a simplistic representation of one of those buildings. Now, we first looked at the building form, the shape, and the arrangement of the buildings. That is, the arrangement of buildings in that just general shape. So it had all three buildings that we were going to look at had a central core and then two wings that were sort of designed like that. The pluses, minuses, and zeros are just to give you a sense of pressure, air pressure, as a result of air moving around the building. 0 is neutral or ambient air pressure. Positive is higher than neutral. Negative is lower than neutral. And there's a greater negative. So 2 minuses means more negative than a single negative sign. And if we asked, so wind goes from positive to negative pressure. Remember that too. So air travels from high to low pressure zones. So we started with the simplistic design, and we asked if we could manipulate the massing of the building or the shape, the form of the building a little bit. And the client said, okay, so we did that. Now, with that little change, we noticed that there was a pressure difference. The pressure distribution changed. So remember, wind flows from air, moves from positive to negative pressure. So here it was like that. And then here, what we achieved was a greater negative than we had before. So that was done and this was done in order to encourage flow to go from here to here, to go from there to there, and so on. Basically to encourage wind to go to the back of the building where the pressure is extra negative. Now, there were 3 of these buildings to be placed on site, and how they were grouped or arranged was also going to be something to be considered. So initially, it was going to be placed in a single line, and so we placed the second building, and that didn't help very much because from negative to 0, basically, there's no flow going from here to here because 0 is higher than 2 negatives, right? So this building isn't getting that much wind anymore. We had the third one, it became worse. So the idea here was to encourage winds to get to the last building here and even to the back of that last building, so that all of the windows, if the windows were open, that it would be ventilated. And again, reminding you, air moves from high pressure to low pressure. So we talked to our clients and rearranged the buildings like that. Now, we proposed this arrangement, and what it did create, if you just compare the other, the negatives and positives from the previous slide to the current slide, you'll see that all of the buildings are now sort of equally getting a good distribution of pluses and minuses. So wind can flow from positive on the upwind side to negative on the downwind side. And if windows were open on the two sides, wind would flow through it. So, depending on the internal division, there could be a good amount of natural ventilation. So now all three buildings were sufficiently exposed to winds, and the arrangement encouraged movement between them for natural ventilation, both outdoor as well as indoor. So what would happen was that by moving this building away, we removed an obstruction that was there. And so this allowed wind to flow around the first building, re-engage, and then approach the next building, and then flow around it. This building didn't face a problem because winds were coming from here, and there was nothing obstructing winds reaching the area. So it's interesting, the things that we have to do to get our solutions to the client. And when it comes to wind engineering, the key is early design, because it's always easy to make a change and design your projects as you need in advance, rather than have to build it, face a problem, and then try and change it or retroactively try to fix something. So that was the end of that demonstration, and that brings me actually to the end of all that I had to share with you today. That was a long session, I know. Wind engineering is a niche yet vast field, and to condense it to an hour really doesn't do justice to you, but I hope you found it useful. This webinar series is such a great platform to expose you to so many unique ideas, avenues, and prospects that most people don't have easy access to. So thumbs up to the organizers, and thank you for the opportunity. I hope you really do the best at this moment and take yourselves to the best of places in your future. All the best to all of you, and thank you once again.
So now we can move on to the doubt clearing section. Miss, first question, which software can be used to analyze wind hazards?
It really depends on where you're working. A lot of companies do have their own programs, just built based on their experience, backed by their experience in the real world, their experience in the wind tunnel. So honestly, I wouldn't recommend a software to evaluate hazards. It's a pretty risky thing to do because hazards or dangerous situations are typically caused by wind speeds that are infrequent, gust that is also difficult to model, let's say even in CFD. So in my limited experience in the structural side of things, I would say, well, the short answer is the software, if any, would depend on each company's or each institution's experience. And if someone is using a software, generally the industry recommends that they be very, very experienced so that they can judge the results carefully.
Thank you, Miss. And the next question is, for high-rise building, is CFD method or scale modeling is more accurate for modeling?
What was that, CFD or? I think your voice broke off.
Scale modeling is more accurate for modeling.
I don't think I heard that again. Sorry, I'll keep quiet. And can you repeat the question, please?
For high-rise buildings, is CFD method or scale modeling is more accurate?
Scaled modeling. Okay, understood. For high-rise buildings, again, it depends on the purpose. So if you're looking at, in general, for structural studies, if you want accurate numbers, especially when you're dealing with very high-rise buildings with a lot of complex flows around it, if it's a very simple structure, like a rectangle, a cube structure, you could get away with CFD, but only to look at speeds around it. There are advanced programs that can give you structural calculations also. But then again, because you're dealing with such a complicated issue, the computational time might be tremendous to get at structural loading results. I would say scale modeling is the more appropriate way to go,
the robustness of that method.
you, Miss. And the next question, which hazards are most often when working in high wind conditions?
Which hazards are most common? Is that the
Yes.
question, Goldie?
Which hazards are most often when working in high wind conditions?
It's a difficult question to answer. Maybe I didn't understand the question properly. I don't know if this will answer exactly what you were question that you had intended to ask, but in a high wind environment, hazards could be some of the examples that I showed you. Actually, it could be because of if it's a storm, it could be because cladding or glass windows break. It could be because you're walking on a street and it's a pretty high wind condition, and the example that I showed you, that temporary structure falling over people. It could also be problems where nothing falls on you, but you lose your balance because it's so windy and you're not able to balance yourself. We call them gust effects on pedestrian comfort, on people comfort, and these are low frequency but very strong, very sudden bursts of winds that happen in high wind environments, and it could affect a person's balance.
Okay, thank you, Miss. The next question is, could wind channel provide accurate result to wind load distribution over the building?
Yes, I think I explained most of that answer earlier, but yes, load distribution along across the facade of the building and that's it's done in a method called high frequency force balance, where you'd look at pressures across. It's high frequency pressure integration, HFPI, where you're looking at wind pressures across the facade of the building. You'd get point pressures, so point loads, and each of those point loads would be associated with a tributary area, and then you integrate over the entire facade to get a design load for or kind of load distribution across the building.
Thank you, Miss. And next question, after BTech in civil engineering, which course should we choose to get into this field?
This was a point that I was trying to make in one of my beginning slides. I think if you're truly interested in this field and this is all you want to do, then you could try for a wind engineering course. IISc Bangalore offers I think an aerospace or aerodynamics course. I'm not sure what the exact name is, but the universities, you can go back and look at the recording of this video. Those universities that I listed offer aerospace and aerodynamic courses that if you wanted to do a master's in, you could pursue. There are obviously many universities internationally that offer specific wind engineering courses. It's more established in some of these other countries because they've had more wind problems than we have had in India. So where the necessity is the mother of invention, right? So a lot of these foreign universities do have a lot of prospects in wind research. One of those universities is where I went, Concordia University in Montreal. They have a great wind engineering research lab and programs associated with it. In Canada, there's another university called Waterloo University of Western Ontario. That's somewhere you can look at if you're interested in international university. ETH Zurich even if you just type in ETH wind engineering Switzerland, you'll get to this university. It's also pretty established. There are several other universities in the US as well. Kansas State University has an architectural engineering program. So even if you wanted to just explore universities outside of India, you could just type in architectural engineering or building wind engineering. These are some keywords that you can actually use to find research projects that you'd be interested in, and then pursue those, apply to those universities if you'd like.
Thank you, Miss. And the next question,
And the next question, keeping in view the balance between budget and actual needs, does it depend on the height of the structure or the traditional behavior of that area? Is it,
Pardon?
keeping
was that the end of the question?
Yeah, yes, miss.
Okay. Is it the height or the traditional nature of the building? Is that what was asked?
Keeping in view the balance between the budget and actual need, does it depend on the height of the structure or the traditional behavior of that area?
By traditional behavior, I'm going to guess that you meant weather, climate conditions around the area. So is it the ambient weather climate conditions that affect the building, or height? I'm guessing that that's a question. If that was, then it's a combination of both. I mean, in terms of cost and functionality, you do want to design the building in a way that it's safe in the end. And if you, in the long run, it might actually save the project team a lot of money if it's designed well right from the beginning. Now, the other interpretation could be that you were asking traditional behavior of the area. I don't know if you meant how people use the building or how people behave around the building. If that is the case, similar answer. Sometimes when it comes to structural and cladding are a totally different thing. You're basically trying to design the building to be strong and withstand wind. So it has nothing to do with how, let's say, if this was the intent of your question, it has nothing to do with how people behave around the building. But you just have to simply design the building to be as wind responsive as possible. And it actually, especially if you go through wind tunnel testing and more experimental methods like that instead of code, when code-based methods, when it comes to complex designs, you have to know codes are very conservative because it can't, a code cannot provide you all hundreds and thousands of scenarios that you would face. So it gives you some generic shapes. And then if you go through experimental methods, you'd be getting loads customized to your design, not a general shape. And so that helps a lot in terms of using just the appropriate amount of material without being extremely conservative. There is some conservatism involved, but not too much. So there's some savings there. So that's the structural and cladding side of things. General behavior of the area in terms of people is more of a concern when it comes to pedestrian level, like wind comfort. In those scenarios, let's say you're finding that the building creates a big wind problem in a certain area near a building. You have to kind of use your judgment to understand the usability of that area as well. Maybe it's a back alley of a building where nobody goes. Maybe it's a swamp near like a marshy area where nobody goes. If it is not going to be accessed by people and the building is causing a huge wind problem there, then maybe it's not worth putting in a lot of effort to design the building to solve that problem. So you kind of look at you have to look at all of these scenarios and use your wise judgment to see if the solutions are worthwhile.
Okay, thank you, Miss. And the last question, is there any process to nullify the effect of any cyclone or turbulence?
There is not really. These are beyond our control. Natural elements like cyclones or hurricanes, that it's beyond our control. Typically, if it's like a usual like a residential building, there is a certain strength or speed of wind that you would design it for. If it's a hospital building, then it's more important that people are more dependent on that building. For example, if it suddenly gets destroyed in like a low wind speed, that's not good, right? Too many people depend on it. It's a bigger investment. So those kind of buildings are designed for even stronger winds. Nuclear reactors, for example, I think, if I remember correctly, are some of the buildings that are designed for the strongest winds, because you do not want a nuclear reactor to be destroyed at any point of time, if possible. So it depends on the kind of building that you're looking at. But I don't think there's a way to nullify hurricane level events altogether for regular buildings.
Thank you, Miss. Hope we covered almost all relevant questions within the time limit. Thank you so much, Miss, for taking such an excellent webinar. Thank you all for your participation. We will be back with our next webinar on 7 June 2020. Follow up our webinar series and let's learn together. Thank you.
Thanks, everyone. Take care.